T and Z. Students are confused. When do I use a t-score? When do I use a z-score? They're kind of interchangeable, so which ones do I apply for which questions? Let me give you guys a flow chart that would be helpful for the rest of the year and knowing whether to use a t-distribution or a z-distribution. There are two different types of inference. Are you doing inference on proportions for a sample, like the percents, or means? Are you taking an inference for some average? Proportions, they're always going to use a z-distribution. For means, there are two different cases. And it has to do with the amount of error. Why does a t-distribution have fatter tails, as I had you guys explain in practice yesterday? On the screen, you have a t-distribution compared to a z-distribution. Why does the t have fatter tails? Smaller sample size, which leads to more error, right? I have more variability because of the smaller sampling. Another reason I might have more variability is known or unknown parameters. In this previous question, I was using the standard deviation of the sample as an estimate of the overall variability. I only knew the standard deviation of the sample data, not the population in whole of itself. When I'm using a standard deviation of the sample as an estimate, doesn't that mean more error? I'm using an estimate of the overall variance taken from the sample. More error. I either know the variance, know the actual population standard deviation, or I don't. I was given the standard deviation, I was given the variance of the population. Or I can only use the sample standard deviation as an estimate of the overall variability in the population. When I have to use an estimate, I have more error. It also goes in terms of sample size, like Jack said. For a sample size that's greater than 30, what happens as I get this bigger here? What happens as I move this slider and increase the sample size? What's going to happen to these two distributions? And after about 30 as a common convention, aren't they approximately similar? Yeah. So I have a large enough sample size, or I know the overall variability given by the population standard deviation, I can then use Z. Because I have less error. I don't need to estimate the variability with the sample standard deviation. And I have a large enough sample size so that central limit theorem says that my distribution is normal anyway. Feel free to use a z-score. If I have to use my sample standard deviation as an estimate of the overall variability, or I have a sample size that is smaller than 30, and small sample sizes produce more error, the t-distribution, because it accounts for that large amount of error with the fatter tails, is a more appropriate model. Okay. Let's do this next. Today's focus is on creating and interpreting confidence intervals for means with known parameters. I know the population standard deviation. So what do you think I can do? Use a z-score or a t-score? Z. Very similar, but a little bit different. Rather than a t-score with a t-distribution, we're using z-scores today for making our interval estimate of population mean. So I am trying to create a confidence interval for a population mean, so I take a sample. That sample is known as x bar. Because sampling is random, I have to add and subtract some margin of error, some mode. That margin of error is how many standard deviations that I can look up by using a z-score. A z-score is how many standard deviations capture some part of the distribution, 98%, 95%, 99%. How many standard deviations we have to add on to our sample estimate to capture 95% of the distribution. Standard deviation of our sample mean. How many standard deviations of that do I have to add on for the margin of error? Will be our total confidence interval. Since I know the overall population standard deviation, the standard deviation of our sample mean is sigma over root n. All right, pull out your formula sheet, please. Let me identify where this is at on your formula sheet. On the side that says confidence intervals. Confidence intervals for means with either known or unknown parameters are these two formulas here. Known parameters, unknown parameters. Look at those two formulas. They're very similar with a couple of minor discrepancies. What makes these two formulas different from each other? Z or T? Why are they using a z-score for known parameters and a t-score for the unknown parameters? What else is different about those two formulas besides z and t? The standard deviation. In the t-score for the unknown parameters, I'm using the sample standard deviation as an estimate of the overall variability. In the known parameters, this sigma represents the population standard deviation. I no longer have to estimate the variability with my sample because I'm given the overall population variance. I don't have to estimate, that means less error. Less error means we have z-scores rather than t-scores. Does that make sense? Now, I don't cover these types of confidence intervals a whole lot because to me, they're not really practical. Why would I create a confidence interval for a population mean if I already know the population standard deviation? That doesn't make sense. To get the population standard deviation, wouldn't I have to know the population mean itself? So would a confidence interval really be necessary? I don't really think so. These aren't super practical, so I don't cover them super in depth. I think a t-score sample estimate for the overall variability is a much more practical application, but they are covered in introductory stats courses, so I do need to cover them. Let's try this type of confidence interval question using our known parameters formula with z-scores rather than t-scores. Reading through this question, conservationists are interested in how a recent population of gray wolves that was reintroduced to Yellowstone National Park is thriving. Over the last several decades, gray wolves in the American West have been in decline and almost become extinct. So conservationists recently reintroduced a small population of gray wolves into the national park, and they want to check to see what their overall health is. Are they thriving or not? So these conservationists randomly sample 50 of the wolves, and they find an average weight of 112 pounds. If their weights are bigger, probably more healthy than if their weights were too small. Previous studies have shown that the weights of gray wolves are normally distributed with a standard deviation of 16 pounds. So I have some prior studies, I have some prior data. We know a lot about these wolves, and I probably know the overall variability of this population. The overall population standard deviation for all gray wolves is 16 pounds. Create a 99% confidence interval for the average weight of gray wolves in the national park. Let's identify what we've been given and how we're going to attack this question. Underline some of these given values. The 50 refers to what?
The sample.
Sample size. We sampled 50 gray wolves that were reintroduced within the national park. Sure. They find an average weight of 112 pounds. Does that 112-pound weight refer to some of the wolves or all of the wolves? Is it the wolves in the park, the sample, or all the wolves in general?
The sample.
The sample. So this would be our sample estimate of the average weight. In looking at the 50 gray wolves, our sample average was 112 pounds. I want to create an interval estimate for the overall average weight for all the wolves in the park. Studies have shown that weights of gray wolves are normally distributed with a standard deviation of 16 pounds. Is that the sample standard deviation or the population standard deviation? Does that refer to the standard deviation of some of the wolves or all the wolves? All? How long you're saying all? I would agree with that. Why would it be all? Right, not some of the gray wolves, all the gray wolves. I've done research on this species, this population, and I have a pretty good estimate of the actual standard deviation for the entire population of wolves, right? So this would be not S, but sigma, the population standard deviation. We're going to create a 99% confidence interval for the average weights of the gray wolves in Yellowstone National Park. And come back to the flow chart. We're doing inference on proportions or means, percents or averages. Averages, do I know the variance or do I not? Am I given the population standard deviation or do I have to use a sample estimate of that value? I know, so we're going to use a z-score. On your formula sheet, we'll be using the confidence interval for means with known parameters because it fits my values. I have the actual population standard deviation as a known parameter, the known variance. Working on your formula sheet here, we're going to do x bar plus or minus the mode. How many standard deviations do we have to add on to capture 99% of the distribution? That would be x bar plus or minus some z-score times the standard deviation in x bar, which is sigma over root n. Formula from your formula sheet. Before I plug everything in, what's the z-score for a 99% confidence interval? You can also look on your formula sheet and find it. We're using the z-scores. I can have these common z-scores found on my formula sheet. For a 99% CI, what's the z-score on here?
2.575.
That's going to capture 99% of a normal distribution. Within 2.575 standard deviations of the mean lies 99% of the distribution. So 112 plus or minus 2.575 times our standard deviation of the sample mean, which is 16 over root 50. Let's find the margin of error first. 2.575 times 16 over radical 50, 5.8266. Again, what is this known as? What I have to add and subtract? Sure, that's the mode. My estimate, based off the 50 wolf samples, shows an average weight of 112 pounds. That's no more different than the actual average weight for all the wolves in the park than 5.8266 pounds. No further than that away, that many pounds away from the actual population average weight. So 112 minus the mo is 106.1734. And we'll add it to find the right endpoint. 117.266. Meaning that we are 99% confident that the actual average weight of the gray wolves reintroduced to Yellowstone is between 106.17 pounds and 117.83 pounds on average. Let me pause here. Questions so far? All right. Well, say these researchers, that's not good enough. There's too much error. I want to reduce the margin of error, but still have the same level of confidence. I go back to these researchers, it's not good enough, I'm sorry. I want to be as certain, but with a smaller interval estimate. I need to decrease the margin of error while still being equally as confident. What would I have to do to make that happen? Larger sample. In this example over here to the right, our researchers say, I want to be within 3 pounds with 99% confidence. My margin of error is a little less than 6 pounds. What sample size is going to be necessary so that we're no further than 3 pounds away and still having 99% confidence? Like Jack said, we're going to have to increase the sample size. Larger sampling, smaller error. Let's talk a little bit more about the formula to find the sample size necessary for a given error using means. We've done this before. We've just used the proportions estimate. On your formula sheet, that would be on the back page towards the bottom. Let me pull this up and share so everyone can see. We've used this formula, I believe, that says for proportions. What sample size is necessary for a given or allotted error value? Now you have this one to use for means. Let me explain more about where that formula comes from. In your margin of error formula for confidence intervals, the margin of error is given by this piece, what I have to add and subtract. I want that margin of error to be no more than some allotted error value that we've been given. I want our z-score times the sigma over root n sampling standard deviation to be no more than some allotted error, at least equal to or allotted error. We're trying to find the sample size necessary to make this margin of error no bigger than our allotted error. Which variable do I have to solve for to find the sample size? We're going to solve this. Or let's put our margin of error in terms of the sample size. E is the given error. I want to be no more than, say, for example, 3 pounds away for the average weights of the wolves, right? So let's solve for n. To continue to solve for n, I'm going to divide both sides by z. Move the z over to the right by dividing both sides by z. Now I see a proportion. To solve proportions, I'm going to cross multiply. Set our two cross products equal to each other. Root n times e is one cross product. Sigma times z is the other. Keep solving for n. I'm taking the square root of n times e, so how do I get rid of e? By both sides by the error. And lastly, I have the square root of n equal to this sigma z over e formula. To get rid of the square root and solve for n, what do I do to both sides? It's the opposite of square rooting something. Squaring it. Square cancels out the square root, and here's that formula from your formula sheet. Sigma times z over the allotted error given squared. Pretty much the same thing there. Using this formula, we can now answer our researcher's question. They want to have a more accurate interval estimate. They want to be no more than 3 pounds away while still maintaining 99% confidence. Using previous data, how many wolves must be sampled and their weights taken so we are no further than 3 pounds away from the average weight and maintaining 99% confidence. So z-score for a 99% confidence interval. Same one from earlier. The standard deviation of the wolves, their weights was 16 pounds. And my allotted error, I want to be no more than 3 pounds away from my margin of error. No further than 3 pounds away. Let's see what we got here. N equals 2.575 times 16 for the standard deviation over the allotted error of 3 pounds, 1b squared. Looking up on the screen. I'll share my calculation again with everyone. I'm going to have a hard time sampling this exact number of wolves. I have a sample size of exactly 188.604 cubic. Obviously, going to have to round to some whole number. So I want to round up or down? Up or down? Up. Why up? Even if it was 188.06, I'd still round up. Why?
Because you can't have part of a wolf.
Right. What if I make it 0.06, so it's actually closer to 188, Isaac, than 189?
You're under the stuff.
If I go down, then I am no longer within the 3 pounds of error, right? Smaller sampling is going to increase the error. I'll never round down. I always round up.
I was trying to say.
If I round down, I'm not within the 3 pounds of error they allotted me. Can't sample a fraction of a wolf, and I also can't go down and inadvertently increase the error to be outside the margin of error that I was allotted.
Wolves.
Cool.